All right, good afternoon, everyone. I'm gonna apologize at the beginning. I have a nagging cough, so I'm gonna have a cough drop, so it might, um, but anyways. Good afternoon, my name is Michael Baranowski. I'm with Dewberry. Today I'm gonna be talking to you about a fun little project in North Carolina flown for the USGS. Just a quick background about Dewberry, specifically our geospatial mapping and survey. We have over 150 geospatial professionals and 150 survey professionals. Um, the geospatial department has staff located throughout the U.S. Our main offices are Tampa, Fairfax, Denver, and now we have staff in the Carolinas in Charlotte and Raleigh. One additional thing, before the North Carolina Sparta project was flown, we didn't own our own sensors, but in 2022, we made a big purchase, and we now are the owners of 3 aerial sensor platforms. So a little introduction. A recent seismic event near Sparta, North Carolina illustrates the need for emerging high-resolution LiDAR applications. This project really meant a lot to me as it brought me full circle in my geospatial career over the years here in North Carolina. I'll explain a little later at the end. As most of you know, the USGS is actively engaged in the collection and publication of high-quality aerial LiDAR at a minimum of QL2 for the contiguous US. As LiDAR technology improves, the following is now a reality. Achievable pulse densities and vertical accuracies are increasing well beyond QL2 specifications. Generally, the costs for increasing LiDAR quality are decreasing. With the newer technologies offering greater terrain resolution, applications previously unavailable or cost prohibitive to LiDAR survey have been emerging. High-resolution LiDAR data provide the gateway to evaluate subtle changes in the terrain morphology, such as karst features, subsidence, uplifts, and fault lines. In the early morning of August 9, 2020, an earthquake measuring 5.1 megawatts on the Richter scale occurred near the small town of Sparta, North Carolina. The earthquake was a shallow, 2.3-mile deep event, not associated with any active fault line. However, the effects of the quake were felt as far away as Washington, D.C. and Atlanta, Georgia. This earthquake was felt by many people and for quite some distance. I remember exactly where I was the morning it happened. My family and I were up visiting the grandparents in Hendersonville, North Carolina, which is about 110 miles southwest of Sparta as the crow flies. I had literally just stepped off the raised porch of my parents' house when I heard my mom, "Oh my gosh, what is happening?" My dad's like, "Oh my gosh, that's a earthquake." And so it was quite an event. And I'd experienced earthquakes before living in Panama, but if you haven't experienced it, it's just a really surreal event where it's just like time seems to stand still while everything's shaking around you. It's just quite a surreal experience. So this event was very big, especially for North Carolina without having active fault lines. Local and national news media services photographed the aftermath and then reported lots of damage. So here's just an example of one of the national articles showing a food line in downtown Sparta. This is a close-up of the project area. So the red is the USGS area of interest where the fault line occurred. The LiDAR collection was approximately 100 square miles. Hopefully this video will play. This one I found online of a nail salon in downtown Sparta. Might not play. Okay. It just shows the intensity of the earthquake. All the chairs fell over. Even the camera fell off. So it's quite a significant event to happen here in North Carolina. Additional USGS publications. As you can see, we weren't alone over in Hendersonville. Many people felt this earthquake. In the Carolinas, Virginia, even people reported feeling it all the way up to Ohio. Looking at the modified Mercalli intensity map, the earthquake has intensity contours of strong and moderate, which are quite significant. Now, a little about the LiDAR data acquisition. As many of you here know, the state of North Carolina has an amazing LiDAR program. And between 2014 and 2018, all 100 counties in North Carolina now have QL1 and QL2 LiDAR coverage. Thank you, Hope. That's quite an achievement. for North Carolina. This area fell into phase 4 of the LiDAR program and was flown at QL1 density in late 2016 using Geiger mode LiDAR. So, of course, being 2016, the data did not map the recent seismic event, but provided a great comparison data set for before and after research. Dewberry was tasked in 2020 to collect very high-density QL1 LiDAR for approximately 100 square miles in the vicinity of Sparta. Like I said earlier, Dewberry had not made our sensor purchase, and at the time, so we were able to select a great subcontractor, Servtech Solutions out of Tampa, Florida. They flew the up-to-date Optec Galaxy T2000 sensor with swath track technology. And as you can see from the chart, the data was flown at a very low altitude with a 60% swath overlap, and the goal was for a minimum of 24 points per square meter, and this was achieved throughout the AOI. Here's the control layout for our ground survey, which I plotted myself. There were 23 NVA points, 7 VVA accuracy points, and the points were used to achieve USGS base LiDAR spec QL0. Ground surveying using GPS and mountainous terrains really pushes the limits of the technology. In order for Dewberry to mitigate these challenges, Google Earth was used, and available North Carolina ortho imagery were also used for the control plan. Google Earth, in my opinion, is such a great tool when creating the control plan. We were lucky in this project as there is extensive street view collection, and using the 3D terrain, you're able to pan, interground view, and street level view to check line of sight, to strategically place all control points, and using methods in Google Earth, you're able to achieve optimal spacing and field of view to make sure the GPS rover has unobstructed views and collect the highest amount of GNSS satellites possible. This is all very critical in mountainous terrain. Another great use of Street View is to make sure there are not overhead power lines where control points are placed. For this project, I take pride in my placement of the points because only one survey point was moved from the original placement, and that was due to a location picked on private property. So spending a little bit more time on the front end with the control plan can really go a long way in helping the surveyors when they're out in the field. This is a quick overview of some of the statistics with the control points. And then a little bit about calibration results. From this chart, you can see we were able to meet the requested point density and QL0 vertical accuracy. On the right, you can see an overview of the DZ ortho. This is now a close-up of the urban area showing the alignment of the building roofs. And this is also a post-calibration screenshot of a roof showing the horizontal alignment of 4 flight lines at the peak of the roof. Ground density was also an important part of this project. As I said last slide, we met and exceeded ground density. Taking a look at this ground density raster overlay with the ortho imagery behind it, you can see consistency even in a thick pine forest. Here's a good example. So if you're looking at the imagery here, you can see a dense planted pine forest, and then here is a picture of the view of the LiDAR. As you can see through the intensity image, you can see that all the pine trees. And then this is a quite impressive profile showing the penetration and the dense ground points. So now the fun part, analysis and results. Since North Carolina has a great before event LiDAR from 2016, comparison studies were performed. USGS geologists were able to do before and after comparisons of the ground DEM to locate fault lines present post-earthquake. All new fault lines are visible in the new 2020 collection. And so I'm going to show you some before and after maps, and then hopefully side-by-side comparisons of the 2016 DEM with the 2020 DEM. So this might be a little bit difficult to see here, so I'll cycle through. But if you look in this image, the arrows with the red and the blue are the location of the fault line that's now visible. Oops. This is a little closer. This is probably a little better. Again, it's probably a little better once I get to the intensity imagery, intensity comparison. This is a good picture where you can see the different intensity values, the fault line that is now present in the DEM, and then I've got a good screenshot. There you go. So this line going through the fields all the way into the road. is the new active fault line that is now visible in the DEM. And this is from the USGS study showing the location of the fault line. An additional comparison of the pre-earthquake QL1 LiDAR and the post-QL1 LiDAR. Some additional screenshots. If you look here in this image, you'll see the road and the fence line. There was also quite significant damage where the fault line goes under this road. It actually ruptured the water line, broke the fence, did quite significant damage to the road. And you can see when we flew the LiDAR that they had already repaired the road, and you notice the difference. In addition, this is the viewing the same DEM in Global Mapper there. I think I have no. So, but that's again, you can see the fault line through the middle of that. In addition, the fault line continues into this commercial area, and it shows quite significantly. That is a parking lot in the build, and then the fault line went even under the buildings, and you can see quite a bit of vertical separation. If you look at the profile of the DEM, you're seeing about maybe even a meter vertical difference where the fault line is. I can't go without mentioning the study and great publication from Paula Figueiredo and team. That included both articles and impressive poster presentations. So here are a couple more pictures with her permission to show you from the study, and shows significant damage to the road that I was showing you earlier. That's where the water main broke and the road started to buckle. They also, right after the earthquake, went out with a UAV, flew imagery and LiDAR, and they also did another comparison with the UAV data. So if you have more interest in this, definitely, I've referenced the articles and the posters. It's quite a good presentation. So, lessons learned. Temporal challenges. North Carolina Sparta event was no exception, as earthquakes are extremely rare in the area. The initial quake occurred in the mid-morning on a Sunday. It was difficult to mobilize authorities to begin to determine what was happening. Once the quake was realized in a remote portion of North Carolina, the USGS needed to determine how to proceed, what data to acquire, and how to acquire the required data in an efficient manner as possible. Then to mobilize the personnel and equipment to a remote area and conduct both ground and aerial surveys in a time-sensitive manner. Dewberry assisted the USGS by quickly identifying the available data sources, evaluating the quality of the data, and by reviewing available LiDAR technologies to resurvey the area. Terrain challenges for LiDAR collection and checkpoint survey. Dewberry determined the optics sensor was the best sensor to map the rugged, dense vegetated terrain. To achieve the high ground penetration required for the survey, it was determined that 60% overlap was needed, along with 30 high-resolution survey ground control to assure vertical accuracy. Ground surveying using GNSS and mountainous terrains pushed the limit of the technology. As I said before, to mitigate these challenges, we used Google Earth in the control plan. Remote accessibility and vegetation were also issues. The area around Sparta, North Carolina is both remote and mountainous. Once outside of the immediate population area, Sparta, there are few roads through the heavily vegetated terrain, led to several challenges during the LiDAR collection and personnel deployment. There were few difficulties encountered for the control collection. Dewberry picked good locations for the control, and North Carolina has a great VRS RTK network. So of all the points collected, only 3 had to be static GNSS surveys. So as I said before, this project kind of went full circle for me in my career here in North Carolina. So I came across this picture when reviewing the Dewberry survey photos, and it really made me think about this. So after graduating college, I started in the survey department at Wolpert from 2007 to 2011. One of the many field projects I worked on included some height modernization projects for the North Carolina Geodetic Survey. So in 2009, when I saw this photo, I knew for certain that it was one of the monuments I had helped dig a hole, fill it with concrete, putting the monument in the concrete, and then performing all the GPS observations. So now look, 11 years later, I'm at another company where we use the same monument that I helped establish. So if there is a life lesson to take from this, in the geospatial world, make sure you always take pride in your work and give 100% because you never know. Maybe 10, 20 years down the road, you might actually be involved with a different North Carolina project that references or uses the data from your former work. So this is just a little brief, and then Wolpert, that's an NGS data sheet. So references, and this is a cool half-a-meter dim of Stone Mountain State Park, which actually was in the AOI, the area of interest. So a lot of cool data came out of this. And I want to thank Al Carlin, Andrew Peters, who also helped. We wrote an article for Lidar magazine, so if you look there, it's also published there. So thank you. All right, any questions? All right. The USGS used it for a study, and also I think the North Carolina Geological Survey also used it for. I think it's just for their studies and researching the before and the after, and what's visible in the aerial lidar and what they can achieve from that. I think as well they're probably even comparing the difference between the aerial and the UAV lidar to see which would be the most cost-effective way to review when an earthquake event happens. Yeah, just really like that field area around the yeah. Let's see. I think it was on that one chart. It's quite low. Altitude, there, 1,000 meters. No? It was still, so the UAV was fairly quick. You'd have to, Paula would know that. I can't remember when they took it like within weeks, but ours, of course, went through the USGS and contract. So let's see, the earthquake happened, when was that? The earthquake happened in August and then went through contract, and we didn't fly it until December of that year. All right, thanks.